Okay, welcome everybody. We got few minutes, couple. So I'm going to try and adjust the frame of view so you can see clearly. For those of you who are online, can you please let me know if you can see the board well? Is this zoom enough, or do you want me to close my laptop closer or farther? Can someone please type? The board is fine. Great. Thank you, Natasha. This works. It's good. You can hear me. Krina, Chelina, so many of you. Thank you so much for spending your afternoon here with me. And the credit for this session actually goes to Miss Choi. I'd like to recognize her because she is the one that made me familiar with this technology. I didn't know, and she did a session yesterday, a wonderful session, and she will be focusing on the problems part of it. I'm going to go more over the overall concepts and how to apply them in individual scenarios. And feel free to type in your questions, guys, and I will be, so is it 1 more minute? I should wait for 1 more minute, elements. You will be fine. I know the first quiz is a little unnerving because you don't know the rigor of it or what will be asked, but I'm sure you'll do fine. All right, another few seconds to go here. All right, it's 2 p.m. Good afternoon, everybody. Thank you for spending your afternoon with me. The organization of this study session is I'm going to go over 4 learning objectives, learning objective 1.1, 1.2, 1.3, 1.4. First, I'll give you an overview of the learning objective, and then I'll talk a little bit about the labs that go with it or the problems that go with it. So let's start with learning objective 1.1, law of constant composition. And recall that law of constant composition said in a pure compound, the ratio of masses of elements is always the same. And conceptually, this is pretty easy to understand. If you have a water molecule with 1 hydrogen, 2 oxygen, they react in a mass ratio of 2 grams to 18 grams. So, 16 grams. So 1 to 8 mass ratio. And if it is pure water, it will always have the same ratio. So this concept is rather easy to understand. Now its application comes in 2 ways. The first way is they may give you a particulate level drawing, and then they ask you, and we've been working on some of those, if it is a compound, element, homogeneous mixture, or heterogeneous mixture. And how you tell is by looking at individual component. This you can tell is an element. If I add another type of atoms to it, it is another element. I can also add molecules to it, right? Then it becomes a mixture. If you mix more than one thing, it becomes a mixture. And then you can see if it is homogeneous or heterogeneous by its distribution. The second type of application of law of constant composition, this is the first application, and the second application comes sometimes in problems where they give you 2 different samples of same compound and ask you to find the ratio. So they may give you 2 different samples, and then they ask you to find ratio of a certain element. So if you recall, there was a challenge problem on empirical formula which gave you that in 101.3 gram of a compound which had carbon, hydrogen, and chlorine, they measured CO2 grams, they measured H2O grams, And using those grams, you can get carbon and hydrogen to calculate empirical formula. But for chlorine, they give you two different samples of substance, different amounts. But because you knew law of constant composition, you know that the ratios will be the same. So while there may not be direct questions on law of constant composition, a lot of the questions on it will be application type, where you're using the ratios. So that's as much as I'm going to go over learning objective 1, law of constant composition. Do you have any questions? At this time, I will pause and give you some time to type up your questions or clarification, or even in the chat, if you can let me know, how is it going? Do you want me to slow down, speed up? I would love to hear some comments. I'm going to pause for 2 minutes here so that I give you time to kind of absorb LO 1.1 and ask questions. Yes, Harshita, definitely. The first application of law of constant composition could be in a drawing, in a particulate level drawing, where they kind of draw two samples, like sample 1 and sample 2 of a substance. And they say in sample 1, this is what is there. And in sample 2, this is what is there. Now they may ask you, do you think these are the same compounds? Justify. So when they say justification, they're asking you for an explanation. You will say these two are not the same compounds, because according to law of constant composition, a same compound may have the same mass ratios. And here you see that two of the smaller particles are combining with a larger one, while here 3 are combining with the larger one. So this does not go with law of constant composition. And if it aligned, then you will say, okay, this is the same compound because the mass ratios are the same. So Karina's question, if there are two elements together, would it be a homogeneous mixture? Actually, it depends. If there are two elements together, there can be 3 options, Karina. 2 elements together like this. This would be a homogeneous mixture. 2 elements uncombined like this will be a heterogeneous mixture. And 2 elements combined with each other in the same ratio will be a compound. So it depends. It could be any, but you have to go more to figure that out. Any other questions on learning objective 1.1, law of constant composition? So quadrant way is more giving boundaries to your visual interpretation of homogeneity or heterogeneity. So if you see here, if you use, in this case, they will give you more. So they'll have to repeat it. So if you break it up in 4 quadrants, then you should see same repeating units. Like if you broke it up, let's say this was one particular diagram, and if you broke it up in quadrant, you can clearly see here for us that these are not homogeneous mixture because there are 2 of these here, but 1 of these here. Yes, you can definitely use that. That if the mixture sample was to divide into quadrants, then it's not even throughout. Perfect. I don't see any other questions here, and I think it's a simpler of the learning objective. So I'm going to move on to learning objective 1.4, mole concept. I'm going to do that first before learning objective 2 and 3, because you'll need to know mole concept before we do learning objective 2 and 3. So learning objective 1.2 deals with the, 1.4 deals with the mole concept. And most of you come with the understanding of mole concept. I am just going to give you a summary of the mole concept. So we are now talking about learning objective 1.4, and this is mole concept. And remember, we are not talking about that little furry animal, but we are talking about a chemist's dozen. And because the particles, whether these are atoms, molecules, ions, we are dealing with such small, minuscule particles that we need a large number of them to get any reasonable mass out of it. So our dozen, chemist's dozen, is actually a very big number. It's Avogadro's number. And it is 6.022 times 10 power 23 of anything. It could be atoms, molecules, ions, formula units, whatever. That's why the mass of a mole of substance will vary depending upon what the substance is. There are a couple of things you need to know. Anytime you have gram of a substance, you must convert it to moles before you can get number of particles. And I write particles. When I write particles, it could be atoms, it could be molecules, or it could be ions. It could even be formula units and other things as well. So Avogadro's number means nothing more than a number. There is no direct pathway of converting grams to number of particles. You cannot. You must first convert grams to moles using what? Molar mass, you know this. And using then moles and Avogadro's number, you convert it to number of particles. So what do you use here? You use Avogadro's number. So that is one part of mole concept. The second part of mole concept that is very important for us chemists is mole relationships. And mole relationships refer to how do you read a formula. So if I write H2SO4, it's important, guys. Understand this one more time. This means the number in front here is 1. When there is 1, we don't write anything. So it means in 1 mole of entire thing of H2SO4, there are 2 moles of H, 1 mole of S, and 4 moles of O. This is an important relationship to understand. Let me take another example. If it is PbNO3 twice, then in 1 mole of PbNO3 twice, there is 1 mole of Pb, 2 moles of N, and 6 moles of O. Now, there's another relationship, which is if you write a balanced equation, and I think you can still see it here, correct? If I write balanced equation here, is it okay? Can you guys see it? Can someone please type? Thank you. Thank you. So if I write an equation here, which goes like this, it's 2925. H3PO4. If I write a balanced equation, H3PO4 plus 3NaOH gives you Na3PO4 plus 3H2O. So I have balanced this equation. So in a balanced equation, these coefficients that are in front also tell you the mole ratios. Meaning what it tells you that 3 moles of H3PO4 will react with, 1 mole of H3PO4 will react with 3 moles of NaOH to make 1 mole of Na3PO4 and 3 moles of water. These are important to understand because Using this, if you know the moles of any of the products or reactants, you can figure out the moles of other using mole ratios. And we use this in our Green Chem Lab, Hydrates Lab, in many of the problems. So these relationships are important to understand. So this is learning objective 1.4, mole concept. I will give you a few minutes to think about it and to ask me questions. That's a great question, Gianni. Gianni's question was, if you are calculating moles of MgO, how would you consider the moles of O? Remember, oxygen by itself is O2, but in a compound, it is just O. So its molar mass in MgO will be 1, and 1 mole of MgO will have 1 mole of O, or half a mole of O2, if you must write it in terms of O2. O2 is only O2 when it is by itself as an element. If it is in a compound, then it can be whatever the subscript of O is, 1, 2, 3, whatever. Is that good, Gianni? Okay. Any other mole questions? What elements have to be diatomic? Remember PS half Brinkel. So phosphorus is 4, sulfur is 8, HOFBRINCl. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, they are all diatomic, and they are diatomic by themselves. So when hydrogen is by itself, it's not H but H2. Oxygen by itself is O2. Fluorine is F2, and so on. But if they are in a compound, then they could be just F or N or F3 or whatever the subscript of this element in that compound is. Okay, you're welcome. So I think I'm going to move on now to learning objective 1.2 and then to 1.3. So learning objective 1.2, place this. This board's a little rickety, huh? So learning objective 1.2 deals with mass percent. And mass percent as a concept is fairly easy. When you say mass percent, it is mass of any one component, whichever thing we want to get the mass percent of, divided by total mass times 100. So you will never get a question which says, what is the mass percent of hydrogen, oxygen, and water? Because that's so simple. So typically the question you will get will be application of mass percent. And application of mass percent you saw in Green Chemistry Lab. You also saw in some of the practice problems you did. So let me deal with each of those one at a time. So the application of mass percent, we saw it in Green Chemistry Lab. and I will go over the lab in a minute and its methodology and how we use mass percent here. The other one was in practice problems. So practice problems, the mass percent, the very typical mass percent problem will say there was a mixture of two things. I will take example of N2O and NO. A problem will say there is a mixture which has N2O and NO, these two compounds in there, and then they will give you the total grams of N. From this, they will write some number. Let me make up 52 grams. I'm just making up numbers here. And then they will ask you, what is the mass percent of, they can ask N2O or NO, either. Now, they can ask these questions two ways. One of the ways, they say that N2O and NO are present in equal amount in a mixture where the total N is 52 grams, now find its mass percent. Or they may say they do not know how much N2O and NO is there. It's just been mixed together. It's not certain that they are in 1-to-1 ratio, and now find its mass percent when they are not equal or unknown. Now, how do we do each of these? I will tell you the plan, and then you can solve them on your own. If they are present in equal amount, what you can assume, first of all, is entire 52 grams of N comes from N2O's N and NO's N, right? You know this for sure. And you know, if they are in equal amount, let's say X amount comes from N, then you know 2X will come from here. And you can do 3X amount and convert the 52 grams of N to moles and get X moles, and N2O's moles will be 2X and NO mole will be X then, and then using molar mass you get grams and then you get mass percent. This is one way of doing it when the amounts are equal. If amounts are not equal, then you cannot assume 2X and X. In that case, what you use is a weighted average. And weighted average is like your weighted grades. So we know that 52 grams of nitrogen, all of N is made up from N2O and N. So you convert this to moles, and you know those total moles come from, let's say the total moles, we don't know how much. One, the X moles out of that come from N2O, then 1 minus X will come from NO, right? So 52 grams, we convert them to moles, and we know these total moles are equal to X times molar mass of this plus 1 minus X times molar mass of N2O and molar mass of NO. And then using that, you can solve that. So that is actually an application of mass percent. A little bit complicated one, but that's how mass percent is typically used. They'll give you two compounds made up of same elements like CO and CO2. And then they will ask you to calculate mass percent based upon mass of C, the common element in both of those. Now, green chemistry lab, how did we apply this? I gave you a white mixture, and this mixture had two things in it. It had Na2CO3 solid, which was white in color, and it had NaHCO3 solid, which was also white in color. And I mixed them in some ratio. You didn't know what ratio. What we knew, if you heat up Na2CO3, it remains the same, no change. But if you heat up NaHCO3, then two NaHCO3 break up to form Na2CO3 solid, plus it makes H2O gas and CO2 gas. And you know that the only thing in a mixture that makes H2O and CO2 is Na8CO3. So by figuring out what was the decrease in mass, and this decrease in mass was because of water and carbon dioxide gases that escaped. So if we say H2O plus CO2 grams, right? We got that. This is equal to grams of H2O plus grams of CO2, right? This is what it came from. We know moles are grams over molar mass. So grams are mole times molar mass, right? We say, let's say X moles of water are made. Then see here we use mole ratios. We know when 2 moles of NaHCO3 dissociates, it made 1 mole of this, but 1 mole of this and 1 mole of this. So mole ratio is 1 to 1. So we say it made, let's say, X moles of water. We cannot assume it's making 1 mole because we don't know that there was 2 moles of NaHCO3. So let's say there was X moles, and then we use water's molar mass, 18 gram, plus X. Now you can use the same X. Why? Because we use the mole ratios here, 1 and 1. And this is 44 grams. And this is equal to whatever the mass lost. You solve for X. And Na8CO3's moles will be 2X. And from there, using molar mass, you get grams of NaHCO3. And you divide it by total mass that you got of the mixture times 100, and you get mass percent. So while mass percent on its own is a simple concept, its application can help us solve very many complicated problems. And I would like to give you 2 minutes to ask me questions about the Green Chem Lab or its calculations. But I want to go over the error analysis of this lab as well. So the lab methodology of green chemistry, I will talk in a minute, like what data you had to take and what are the errors. But do you understand how to do calculations based upon mass percent, either in practice problems or in Green Chem Lab? And I'll give you a couple of minutes to think about it. Shoot out your questions. I'm watching. So there is somebody there who is trying to mess this. I'm going to remove them. The big red bear Australian. And whoever this is. Goodness, who are all these people? So Gianni is, no, Gianni is, am I saying your name right? Gianni, yeah. So you wanted me to work out the practice problem with N2O and NO. I know that Ms. Choi did the same thing yesterday. And she did that, but I think she might have done it with the others. So I can do, why don't you go through her problem that she had solved? And if you still have questions, I'll be happy to. But I was hoping that she would take care of explaining the practice problems from the yellow packet, and I will take more time to explain the concept. But if that is your need, I would be happy to address it at the end. How about that? So I do not have, Catherine, a yellow packet with me. Here, would you type what the question is? We will definitely do Hydrates Lab after this, but we need to do one by one, Alan. Hydrates Lab is not gone. We haven't done that yet. And Catherine, can you please tell me what 25A or B are so I can explain the concept to you? You can do the problem. I am not sure if Ms. Choi's live stream videos recording has that. I'm pretty sure she did most of the problems. She did it. Thank you, Forrest. So for all the kids who are asking the specific problems, I think Ms. Choi did a very good job going over the problems, and it is on her videos, and she'd also put the timestamp so you can see where those are. So goodness. Okay. Alrighty. Now, guys, okay, I understand that. So I will answer your hot crucible questions in a minute. Let's now go over the methodology. How you do this lab is you took a crucible, you purified the crucible. It's important so that you burn off the impurities. From there, it could be your hand oil, could be something combustible. Once, and then after cooling it, you weigh it. This is your first mass. Weigh empty crucible. Now what you do is you put mixture in there and you take, this is your second reading. Crucible plus mixture unheated. Then your third reading would be crucible plus mixture heated. Okay, so when you are heating, oh, Ms. Joy didn't do 25, I'll do that then. One by one. Okay, third is crucible plus mixture heated. So if you find the difference between these two, this should be lesser, this should be more, and the difference of 3 minus 2 will give you grams of CO2 plus H2O to be put in this equation over here. The empty crucible is needed for the mass of how much mixture you took. To get the mass percent, you need the original mass. So if you subtract from 2 the mass of empty crucible, you get total mass of mixture. And that is needed for mass percent. So this was the methodology, pretty simple. And now for the equation, the balanced equation was 2NaHCO3 solid gives you Na2CO3 solid plus H2O gas plus CO2 gas. Isn't it 2 to 3 minus 3 to 2? Yes, 2 to 3. You're right. The difference between that, it is 2 will be heavier and 3 will be lighter. More and less. That is correct. Okay, so you get this and that's how you calculate. Now let's talk about error analysis here. So there could be very many sources of error, guys, and this is important to understand here. So what I'm going to do is I'm going to take it from here and erase the practice problems. And I am going to go over to error analysis. So what happens is gases escape when you heat them, right? And while the mixture is hot, the gases are still escaping. So if you weigh it way before you've cooled it, then it does not give enough time to let the gases escape. And then your mass percent will be lower because some of the gases that should have gone out did not go out and your mass percent is lower. So if you do not cool the mixture enough, you haven't given the gases that could escape time to escape. So your percent will be lower. Other error could be, what if you spill some of the mixture, the hydrate, after you weighed it, but before taking the third reading? After you weighed it, but before taking the third reading. So what will happen? You have weighed, let's say, 5 grams of mixture. Now you spilled some, but you don't know. And now you're heating it. So you will say that the mass of spill mixture is the mass of CO2 and H2O. Then you will get a higher percentage. So spilled the mixture after weighing. So if you do that, then you'll get a higher percent. Okay, I will write it in black for sure, Krina. So that is Green Chemistry Lab, and that was application of mass percent. So would somebody be kind enough? I don't have my yellow packet. I can go online and I can do the 25A. Why don't I find it? Let's see what 25A is and then answer that. Somebody tells me that Ms. Joy didn't do that one. So I'm going to go over 25A. Students spilled some hydrates. So this is hydrates. Guys, 25A, B, and C is hydrates. Can we hold off till we do the hydrates lab? Okay. Okay. Now from here, guys, any last minute questions? Okay, so I am going to now move on to learning objective 3. And learning objective 1.3 has empirical formula, molecular formula, hydrates, and percent purity. Okay, let's start one by one. Krina, we will go over the hydrate problem when we do hydrates in a minute, okay? So, empirical formula is the smallest whole number ratio of moles. Remember, it's not mass, it's moles. And because we say whole number ratio, what else we are implying is you use multiplier to get a whole number. You only round if less than 0.1 or greater, less than 0.1 or greater than 0.9. Otherwise, you use a multiplier as you've been doing with your problems. So empirical formula is smallest whole number ratio, like C6H12O6. Empirical formula will be CH2O. Water has same empirical formula as molecular formula because it can be simplified anymore. So ultimately, what you need to do to get empirical formula, you need to get moles of each of the elements in there. Now, empirical formula can be done two ways. You can use mass percent to get empirical formula. And in this type of problem, typically they'll say a compound contains carbon, hydrogen, chlorine, nitrogen, and the percentages were found to be 12%, 12%, 26%, and then whatever remaining is nitrogen, 50 or 60%, right? 50%, 25, 50%. All you do is you assume 100 grams of compound. So what happens is everything, all percentages change to grams. Then use molar mass of each element, get moles of each element, and then use multiplier if needed. Okay. Okay. So using mass percent to get empirical formula is pretty formulaic, straightforward. Now, sometimes what happens is we use combustion data to get empirical formula. And combustion data means we burn things because most of the compounds have carbon and hydrogen. They can form carbon dioxide and water, and then we can get the moles of carbon and hydrogen from that. And these are applicable for two types of compound, or even more, one type that has only carbon and hydrogen. They are called hydrocarbons. And typical hydrocarbons, your fuels are hydrocarbons. Hydro means hydrogen and carbon means carbon. So hydrocarbons are compounds that have just carbon and hydrogen in different ratios. So if they have only carbon and hydrogen, its methodology is to use CO2 grams to get moles of carbon. So grams of CO2, you get moles of CO2, then you use mole ratio to get moles of carbon. Then second thing you'll do, use H2O grams to moles of H2O to moles of H. In 1 mole of H2O, 2 moles of H. In 1 mole of CO2, 1 mole of C. But here it is 1:2 ratio. You get mole and then divide by smallest moles. And I think I skipped that here. I kind of took it in the multiplier, but you must divide by smallest moles. So the methodology is the same for both. So you divide by smallest moles and hope for a whole number. If you don't get a whole number, then you use a multiplier. To get whole number ratio. And that is your empirical formula. And typically in combustion data, what it will look like is you will have a tube in which you'll take known amount of a substance, especially if it has oxygen as well in it. You pass oxygen over it and burn it. You will make CO2 and H2O, and you pass them through U-tubes containing carbon dioxide and water absorbing material. I'm making this diagram because sometimes if they make diagram, then you say, oh, this is a different problem, we haven't done it. Well, problem is the same, its expression is different. So these, they will label it. This is CO2 absorber, and this is H2O absorber. And by seeing the mass increase in each, you can figure out how much CO2 or H2O you have made. So this is when compound has only carbon and hydrogen. Now, sometimes you can be given problems for things that have carbon, hydrogen, and oxygen in them. Now, methodology is little different because with oxygen, some oxygen comes from outside and some is present from within the compound. You can distinguish one oxygen from other, it's the same. So while you use the same methodology, using the same methodology, get moles of carbon and moles of hydrogen, now you have to go further. From moles of carbon, get grams of carbon, moles of hydrogen, get gram of hydrogen. They will give you total mass of the compound. You will need this. And you know that total mass comes from carbon, hydrogen, and oxygen. So to get grams of oxygen, you take total mass, and from there, you subtract gram of carbon plus gram of hydrogen. Now it gives you gram of oxygen. So you have all 3 grams, convert them to moles, divide by smallest number of moles, use a multiplier to get a whole number, and that's your formula. So that is the second way of doing the problem. There is a third way, which is slightly different and only asked once in a while. The third way is, they will say, I'm going to go over here. That was your challenge problem, where they took carbon, hydrogen, oxygen, and chlorine. And you guys can still see that, right? Yeah. So carbon, hydrogen will be carbon from CO2, hydrogen from H2O. And then they said in first sample, out of total amount of sample, this much carbon dioxide, this much water was made. So you can get oxygen by subtracting from total compound carbon and hydrogen grams. So till here it is the same. But for chlorine, they said in yet another sample. So they used a second sample. So what you have to do is use law of constant composition to find ratio of chlorine in this much sample. So if, let's say, 200 gram of sample had 5 gram of chlorine and you had 100 gram of sample here, then you'll use the ratio to figure out how much chlorine will be in that sample. And that was a little challenge that was added, or a little twist that was added to the problem. So these are empirical formula problems. If molecular formula is needed, they will give you molar mass in that case. So you get to get the molecular formula, you need a small multiplier and multiply empirical formula by that. And then to get this multiplier, you get molar mass that will be given to you. Without this, you cannot do it. It will be given to you, and you get empirical formula mass by calculation, because you have already gotten the empirical formula. And then use a multiplier to get the molecular formula. So this is empirical and molecular formula part of learning objective 1.2. 1.3, and I'll give you a couple of minutes. It's a lot of material to absorb. And the next I will talk about hydrates. But let's take a couple of minutes to absorb this material and ask any question. So, Shravya's question. No, Shravya, I think I get your question. So, if it is not written clearly in your yellow packet, that's me being bad. We didn't catch that. A problem will tell you whether it is made of CH or CHO, but sometimes you have to add up the masses of C and H to see if it is totaling up to be the total mass or not. If it is not, then you know there must be another thing in there. And probably I think in one of the problems we did that, where if you add up the mass of C and H, it doesn't total up to be the mass of the total compound. So you know there's something else in there. That's just us being sneaky there. Did that answer your question, Shravya? Sure. Any other questions on empirical formula, molecular formula? Someone who start hydrates. Okay, let's talk about hydrates now. So hydrates, guys, are ionic compounds that have water attached to them. Examples of hydrate are CuSO4.5H2O, CaCl2.H2O, CaC2H3O2.3H2O, and so on. All of these are hydrates. So I did grade your formative assessments. Couple things. Couple of you are writing hydrates as CuSO4 plus 5H2O, even though this means that we don't write it like that. We still write it as dot 5H2O. These are, hydrates are ionic compounds. They're always solid unless you dissolve them in water. So these are solid ionic compounds that have water molecules loosely attached to them. So what happens, because these water molecules are loosely attached, if you heat it strongly, they break apart and give off water. And we use this methodology similar to green chemistry lab by taking a hydrate. If we don't know its formula, we take it and we heat it strongly, figure out how much of the mass was decreased, that is the grams, and from there calculate moles of water and then get the mole ratio. Ultimately, what you are trying to get in there, guys, see, this is always 1. You are trying to know in 1 mole of hydrate or in 1 mole of anhydrate, how many moles of water are there? Let me repeat. What you are trying to figure out in 1 mole of anhydrate, how many moles of water? Or you're trying to figure out, because different problem will give you different data, or in 1 mole of hydrate, how many moles of water. Because if you see in 1 mole of this entire compound, 1 mole of water is there, or in 1 mole of this anhydrate, 1 mole of this is there. So either way, it will get you the same answer. Methodology here varies depending upon the problem, but your ultimate goal is to get grams of water, grams of anhydrate or hydrate, and from there get moles of water and moles of anhydrate or hydrate. Either works depending upon the problem, and then divide moles of water by moles of anhydrate or hydrate, whatever your problem allows. Generally it's anhydrate, to get in 1 mole of anhydrate how many moles of water are combined. Now there are different types of practice problems on it. I will go over Hydrates Lab in a minute, but first let me tell you what all type of practice problems are there. So hydrate practice problems are of in generally 2 broad categories. The one that give you hydrate formula. So you know how many moles water are there. And then other type of problem is where they give you as .x water. You do not know H2O moles. There are 2 types of problems. An example of this type of problem could be, they would say 5 grams of CaCl2.2H2O was strongly heated. How many moles of water will be given off, or mass of water will be given off? If they give you the entire formula, you already know there are 2 moles of water in there. What you will do, you will get the molar mass of this entire hydrate, Ca plus 2Cl plus 2 of the water molecules. Divide 5 grams to get moles of CaCl2.2H2O. Now you know 1 mole of CaCl2 will make 2 moles of water. See, you're using mole ratios again. 1 mole of CaCl2 will lose 2 moles of water. So whatever the X moles you had will lose how many moles of water. And by using that ratio, you can get this type of problem. Second type of problems, which do not give you the X water in there, they can give you 3 different type of data. One type of problem will give you like BaCl2.xH2O, you took a certain mass of it. Let's say you took 10 grams of it. And they will give you mass of anhydrate. BaCl2's mass is, let's say, 5 grams. And they'll ask you to calculate formula. In this case, by subtracting the 2, you can get grams of water converted to moles of water, right? And now you will use moles of anhydrate. So divided by molar mass of BaCl2, get moles of BaCl2, and then divide moles of water by moles of BaCl2 to get that 1 mole of BaCl2, how many moles of water should be there. That's one type of problem. The second type of problem may not give you the formula. Let's say CuSO4.xH2O has 44% water. What is its formula? If they do like that, again, you assume anytime they give you percent, you can convert it to grams using 100. So 100 gram of compound, so 100 minus 44 grams will be whatever grams of CuSO4, right? You convert this to moles, you convert this to moles, and divide water moles by CuSO4 moles to get the ratio. So by adding one more step here, you take it to the same problem as number 1. And then there can be a third way that they can ask you questions. And the third way is they say that you have 10% of water in a hydrate. And then they say that molar mass of hydrate is, let's say, they'll give you some number, 500 grams. Now, how do you do this problem? You know that if it is 10% water, then there's 90% anhydrate. You actually don't even need anhydrate. You can say there is in 100 grams of hydrate, there is 10 grams of water. So in 500 gram of hydrate, how many grams of water will be there? You change it to moles, and then you can write, they will have to give you the formula of what hydrate they're talking about. Let's say they said CuSO4.xH2O. So then molar mass means 1 mole of CuSO4.xH2O is 500 grams. And then you know the masses of each. From this ratio, you can calculate mole ratio from there. Let me summarize this. Hydrates problems can be, ultimate goal is to get moles of water and moles of either hydrate or anhydrate. And there are more than one ways of doing this. I'm telling you the way that works for me, but you guys are good at using ratios in multiple scenarios. You can do that. So one way is they give you the formula. If they give you the formula, then you can go that way. If they don't give you the formula, ultimately you're trying to get moles of water and moles of CuSO4. Give me 1 minute while you look over it. I will, Dan, just give me a second. Okay, can you please, Dan, I'm reading your comment. Can you please re-explain the first example of the unknown mole problem type? I'm assuming this one, Dan, is that correct? Is that the problem you want me to go over? Okay, so in this type of problem, they will not tell you how many moles of water are there. They will tell you overall we have 10 grams of this compound. Then they will give you anhydrates mass, which is just this part, is 5 grams. So we know if we subtract from 10, 5 grams, what do we get? We get 5 grams of water. And you divide it by molar mass of water and you get moles of water. So we know there are these many, right? 5 divided by 18, let's approximate it. About 3 point something, right? Let's say approximate to 3 moles. I know it is not, but let's approximate, right? And we need to now know these 3 moles of water are present in how many moles of BaCl2. Because remember, if we know 1 mole of BaCl2, how many moles of water are present, that is the formula of the hydrate. So we need to now convert it to moles by dividing 5 moles of anhydrate by the molar mass of the anhydrate. Anhydrate is a common term that you can use for the anhydrous part of any compound, right? So if from a hydrate you remove the water, leftover is called anhydrate. You divide by that, you get moles of BaCl2. And now you know in X moles of BaCl2, 3 moles of water are present. So in 1 mole of BaCl2, how many moles of water will be present? And then you'll get that ratio. Does that work, Dan? Okay. Harshita's question, can you please explain the first step? Harshita, did you get it as well? Perfect. I will go over the Hydrates Lab in a minute and the error analysis, but let's take a minute of breather time to let it digest. You're welcome, guys. Sangeeta, could you explain when you're given the hydrate formula, how to solve the problem? So if you are given the hydrate formula, Sangeeta, they have already given you the formula. So the question that they will ask is generally how much water might be produced. For example, they said you have 5 grams of CaCl2.2H2O, and they might ask you how many grams of water will be produced or how many moles of water will be produced. How you do that is you know the molar mass of this entire compound, CaCl2 plus 2H2O, right? You divide 5 grams with the molar mass of this compound, you get moles of this compound. And you know in 1 mole of this, you have 2 moles of water. We know it because of this formula. And because you have converted this grams to moles using mole ratio, you can say if 1 mole of CaCl2.2H2O has 2 moles of water, then whatever moles come out of here will have how many moles of water. And once you know moles of water, you can get grams of water. I'm not doing the math on purpose. I want you to look at a problem and take a minute to think about the problem. Where is it leading you, right? You're welcome, Sangeeta. Okay, now I am going to do the last learning objective, which is % purity. Or learning objective 1.3 is % purity. That's the last concept for today. Oh, I need to do Hydrates Lab. So let's do Hydrates Lab first, then % purity. So in Hydrates Lab, we use similar methodology because we know if we take a hydrate that has some water in it and strongly heat it, it breaks apart into what we call an hydrate, the ionic compound, and the X water. And because it is heated, water is in gaseous state, so it is released out, and we can measure this by reduction in mass. So what we do in a Hydrates Lab, typically your challenge would be, what is the formula of this unknown hydrate? We know there are some water molecules, we just don't know how many moles of water. For doing that, you take a crucible, you first purify and mass. This is your first data. Then you put a hydrate in it, and this is your second data. This is crucible plus hydrate. And then you heat it up, and when you heat it up, water will escape, and you will get, you won't be able to see a difference. It will look exactly alike, but now what you have is anhydrate, and the water has gone out. So this is third data, which is crucible plus anhydrate. This one will be lesser than the second. So if you subtract from second to third, you will get mass of water. And if you subtract from second to the first reading, you will get mass of hydrate. I will, or the person will need to tell you which compound's hydrate it is. For example, I'll need to say it is barium chloride .x H2O. You need to have that data. So you know what is the mass of hydrate, how much water was there. And if from mass of hydrate you subtract mass of water, you can get mass of anhydrate. Or you can also, there are two ways of doing it. Or you can just subtract number, that might be even a better way, go from number 3. If you subtract number 1, this will give you mass of anhydrate. And from here you get moles, because this, if you divide by the molar mass of anhydrate, you get moles of anhydrate. And here you get divide by moles, so moles of water, and ultimately you divide moles of water by moles of anhydrate, and that will be your formula. And most of you did this right in your formative assessment. There are a couple of things, I don't know if it pertains to you or not, but in hydrate, then I'll go back to that. I'm answering a couple of questions here. Whenever you heat a sample, the state has to be gaseous. So water state will be gaseous. That's how it escapes. Very good. Okay, so one thing that you wrote, some of you wrote for 3 moles or 4 moles of BaCl2 to 11 moles of water. This is not right. You need to write it per 1 mole. But the more important thing in hydrates to remember is that you round. So this is the problem. In empirical formula, we didn't round. Unless it was less than 0.1 or greater than 0.9, we used a multiplier. But in hydrates, we round per rounding rules. If the number is less than 0.5, then you keep it the same, drop all the decimal numbers. If it is greater than 0.5, then you round it up. And then if it is 0.5, for evens, you let it be. For odds, you round up. And you'll assume law of averages will take over. Sometimes you round up, sometimes you let it be, so your error will be minimized. So that is Hydrates Lab. Couple of sources of error. You didn't let the crucible cool down enough. Again, you are not giving enough time for water vapor to escape. You will get a lesser percent of water. If you spill the sample after weighing, but before the third heating or after cooling the third time, then there'll be a higher percentage, because lost hydrate or compound will be considered as mass of water removed. So that is Hydrates Lab and couple error analysis. And I can take your questions, let it gel, take a minute or so. Are we good with hydrates, guys? Okay. The last thing we're going to do is percent purity. And because chemists manufacture a lot of things, they make from food items to prescription drugs to industrial chemicals, purity is important to us. Oftentimes, what happens is you may have a sample and it may look pure to your eye, but let's say you have a sample of calcium carbonate. It is what is called chalk. You write with it, right? There might be some sucrose in there, just as a impurity. You won't be able to see it, but sucrose is C12H22O11. Now, percent purity is defined as mass of desired substance over total mass times 100. So in this case, because we are interested in calcium carbonate, if we got grams of calcium carbonate and got the total mass of calcium carbonate plus grams of sucrose times 100, then that is percent purity. Oftentimes, the problem you will get on percent purity will be they will give you amount of a substance that can only be generated from one of these 2 or 3 components. For example, in this case, they will say maybe a 4-gram sample of impure calcium carbonate was treated and 25 grams of CO2 or 0.25 grams CO2 was generated. Only calcium carbonate reacted with CO2. What is the percent purity? If a problem gives you a problem like that, and what is its percent purity? Your thinking is you take grams of CO2, convert it to moles of CO2, and then using mole ratios, they will have to give you the equation because you don't know them yet. You will know it eventually. That 1 mole of calcium carbonate makes 1 mole of calcium oxide and 1 mole of carbon dioxide. Using this ratio, if you know moles of CO2, you know it will be the same moles of calcium carbonate. Then you get moles of CaCO3. Then using molar mass, you can get grams of CaCO3 and then divided by total grams times 100. And that will be the percent purity. And in percent purity problems, the nature of the desired substance and what it produces changes, but the thinking pretty much remains the same. So there will be a special substance that is formed from only one of the ingredients in that mixture, and from getting the moles of that mixture using mole ratio for that substance, using mole ratio, you can figure out how much of that one substance is present in the mixture. And that is percent purity and its applications. Take a minute to absorb it. That question, so percent purity and percent mass. Percent mass may not be for the desired substance. For the desired substance, percent purity and percent mass is one and the same thing. But sometimes you don't have a desired substance in a mixture. It could be for one element or the other element. What is its percent composition? So that is percent mass. So percent purity for the desired substance is the same as percent mass, but percent mass is a wider term. Why? This was like almost enlightening, huh? Okay. What is the difference between percent purity and atom economy? Percent purity and atom economy generally is, they both indicate the same thing. Percent purity is more a lab-based technique. So this uses the lab data because you will conduct the experiment. You'll take a known mixture, you'll make things out of that in a lab and then analyze it. atom economy is a very theoretical based process. You'll be given equations, and based upon those equations, you will be calculating atom economy. No problem, Gianni. No question is too silly. If it comes to your mind, it's worth my attention. Okay, so that is percent purity and atom economy. Harshita, they both indicate the same thing, but one is based more off of laboratory data and one is based more on theoretical calculation. And Ashley. All right, I will have the session open for 5 more minutes for any questions that you might have, but this really is a review for the first quiz. I know you will do great. There is Ms. Choi's solved out practice problems as well for your review and resource. I think you're very prepared. Remember, there are 2 attempts to this quiz. Focus on learning and really building the base right. So as AP chemistry gets more complex, you have really solid grounding to stand on. I am here for 5 more minutes, guys. If there are any questions, type in my way. I will post the recording up, and Ms. Choi taught me how to do time stamping, so I'll try to do that as well. Which question, Gianni? What's the difference between percent purity and percent mass? Percent mass. So percent purity, all of these are very similar relative terms. Related terms. It depends. The difference in the terms comes from the intent of the person that's asking. So percent mass indicates that you are not looking for a commercially viable substance. You're just looking to analyze a mixture and see what are the different things in there. When you talk percent purity, intention is the purer a substance is, the more is its commercial importance. So theoretically, in calculation, there will not be a difference, but the intent is different. In percent purity, it comes more from the manufacturing side, where the purer the substance, there's more value to it. And percent purity might be important in, again, your pharmaceutical medicines, right? You want to know exactly how much dosage of something you're getting, and you can purify it more and more. So I think just the intent where that question is coming from separates percent purity and percent mass. Thank you, guys. Thank you so much. Number 19 on the yellow packet. So I have a question. And my question is, just give me a second. Oh, goodness. Okay. So what was... You may be applying atom economy. I am not sure. Number 19, can one of you who attended Ms. Choi's session confirm if number 19 is solved out by her? Can someone please confirm that? If it is, then I'd rather not. If not, then I will have to. She did it. Thank you, Sangeeta. So, Krina, I am going to refer you to Ms. Choi's link that is on the Facebook group that has number 19, and you can go over that. If you still have questions, Krina, after going over that, I will be very happy to work with you tomorrow during tutorial or brunch. or I will be there a few minutes even before class starts. So by 7:30, I will be there. So you can always come see me in the morning. So you have your questions answered before the session starts, okay? Oh, that's a good question, Sravya. For the quiz, I think because it's your first quiz, Sravya, I am not going to stress you for time. However, I do want you to have a good idea. So what I'll do is probably I'll give you 30 minutes 35 minutes, and then I'll keep extending. I'll ask how many need more time. Our time preparation for AP exam will begin a little bit later, so I don't want to stress you for time. So work with 40 minutes of time, Sravya, and you guys should be good. So have you taken practice quiz? If you've taken, 40 minutes is the time that I think is a good time. So Ashley, Miss Choi's link is posted on the Facebook group. Thanks, Ishani. You guys are amazing. Thank you for spending your afternoon with me. This is amazing. And I thank Ms. Choi again for showing this. This is so much more meaningful and easier. So my parents, oh, okay. So I think, but Ashley, a question specifically for you, you have access to the YouTube, right? So if I were to just, can you email either me or her and we can send you the link back? You are welcome, Karina, Nitin, Hashita, all of you. Ashley, send me or Miss Choi an email and we will send you the link to both our videos and then you can watch it that way. Okay, Ashley? I see, thanks. Okay. You are so welcome. So appreciate your time, guys. Take a deep breath, focus on learning. We got you. You got a lot of support and a lot of understanding here. Our goal is to take you where you need to be. You will be there. All right, I'm going to call it a day and you guys relax and believe in yourself. Okay, I'll see you tomorrow, bright and early elements. Thank you. Bye, Dan. Bye, guys, everybody. Thanks. Oh, you guys are so kind. Bye-bye.